Okay, more induction proofs. This time we've got the function take W and drop W, and we've got the definition of concatenation and the definition of if. We want to prove for all lists XS, take P XS, concat drop P X. If you take all the terms before P fails and then take all the terms after P fails, concatenate them together, that's the same as the entire list. We need to prove this for all lists and all functions. Make sure you justify it, blah, blah, blah. State and prove the base case of the proof of P. Okay, so base case is going to be prove P of the empty list. We need to prove P of the empty list for all functions P. So if you write that out formally, we need to prove for all P, take WP empty list, concat drop WP empty list equals empty list. Okay, let P be arbitrary. Here's the proof. Left hand side is equal to that. Take WP empty, concat drop WP empty. Okay. These rules aren't labeled, so I'm going to label them. I'll call this T1, and I'll call this T2, and I'll call this D1, and I'll call this D2. Take WP empty is the same as empty, and drop PWP empty is the same as empty by T1 and D1. It's okay using multiple rules in the same line like this because these two statements don't affect each other. But if one line is directly dependent on another, as in like I'm doing like two steps at once on the same thing, then you really should do them separately. And then empty concat empty is empty by A1. By A1. Which is the right hand side. Okay, cool, done. State the inductive hypothesis of the proof of P. So that is, we need to assume for some list XS and for all functions P this property holds. So the inductive hypothesis is for all P, all that junk, take WP XS plus drop PW P XS equals XS. So for some list XS. Okay. Where's the next page? It's over here. State and prove the step case goal of the proof. Alright, so step case goal. Better label that inductive hypothesis. There we go. That's terribly blurry. Let me just focus that. It won't let me focus the recording. Well, that's okay, well, there it is. Alright, state and prove the step case goal. So, step case. We need to prove for all new elements X, for all functions P, this property holds with X cons XS instead of just XS. So, take W P X cons XS, concat drop P W P X cons XS is equal to X cons XS. Okay, proof. Left hand side is all this chunk. Take W P X cons XS, concat drop W P X cons XS. Okay, so what can we use to help us? Okay, so take WP. If P of X is true, then the X comes out the front, else we get the empty list. Now, I don't know if P of X is true or not, so I'm probably going to have to do cases here. I'll do two cases where P of X is true and P of X is false. So, case 1, P of X is equal to true. Okay? So if P of X is equal to true, take WP X cons XS is empty. Plus drop PW Px cons xs by T2. And what does this evaluate to? If P of x is true, which it is, I guess I've really skipped a step here because I haven't evaluated what true is. So I haven't evaluated the if statement, so I shouldn't do that. This should become if P of x, then x cons take W Pxs, Pxs, else empty list, concat drop W Px cons xs by T2, and then afterwards I apply I1 because I know P of x is true, or being really pedantic, if true, then, you know, blah 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 blah, write the same thing again, by assumption, or case 1 perhaps, and then I can replace this big if statement with the first term, with the second term here, because we know it's true. So P of x is true. If P of x, then the first thing, else the second thing. So replace it with the first thing. X cons take W Pxs, concat drop W Px cons xs. The definition of true for if got me there by I1. And now we get to play the same annoying game again. So x cons take W Pxs, concat, what does this evaluate to? All that junk. If Px, then drop W Pxs, else x cons xs by D2. P of x is true by assumption, by case 1. So blah blah blah, same thing again. Concat if true, then drop PW Pxs else x cons xs by case 1. And then by definition of if, I can replace this whole thing with just this first term here. So then we get x cons take W Pxs, concat, remember this evaluates first the cons, concat this chunk, which is drop PW Pxs. By something, by I1. Okay. By definition of concatenation, I can bring the x out the front. So x cons take W Pxs, concat drop PW Pxs by A2. And by my inductive hypothesis, I can plug these two things together to get xs. Leave me with x cons xs by inductive hypothesis. Okay. Well, we're only halfway there because I proved it for the case where P of x is true. Now I'm going to prove it for the case where P of x is false. So I guess I'll use the extra additional responses stuff at the end of the exam paper. Here we go. So what question am I doing? I'm doing question 3bi, and then see end of paper for more. Okay, where were we? So now we're going to prove for the case number 2. P of x is false. Don't do what I'm doing. Don't use red pen in your exam paper. You'll really bother us because we use red pen to mark. Please don't use red. I know I'm using red, but don't do that. Forgot where I was now. Proving this thing equals that thing. Alright, so left hand side is equal to, or this rod, take W P x cons xs, concat drop PW P x cons xs. Alright, by definition, I'm just going to do both rules at once here. This term here evaluates to if blah then blah else blah. So if px then x cons take w p xs else empty. Concat if px then drop pw pxs. Drop w pxs else x cons xs. By t2 and d2 used together, replace the p of x with false. So if false, then x cons blah blah blah, write the same thing again. If you wish, you can skip over this part of the video. I'm going to be writing it for another 20 seconds or so. False, then... Maybe I should like speed this up in post-processing, but that's kind of painful. There we go. By case 2. And then if false, then this, else that. So it's going to take the second thing. So we have empty list, concat x cons xs. So I've used the definition of the if statement. So I've used I2 twice. And then empty concat anything is at anything by the definition concatenation. By A1. And there we go. That's the end of the proof. Is it? Yep, yeah, oh, I forgot to say, let x and p be arbitrary. And there we go, it's proof for the case where p of x is true, proof for the case p of x is false, therefore the statement's proven. Doesn't hurt to say at the end, you know, therefore statement holds by mathematical induction, but you don't have to do that, that's probably overkill.